Hello again. This is Math 2233 coming to you from the College of DuPage, and this is the continuation of the lecture entitled Maximum and Minimum Techniques in Higher Dimensions. As always, please be an active learner as you watch this video. When last we adjourned, you were finding the local maximum and minimum values and saddle points of z equals f of xy equal x to the fourth plus y to the fourth minus 4xy plus 1. If you're able to complete this problem, congratulations. If not, I'm giving you a little bit of time to do it right now. You know what to do. Let's see how you did. Okay, well, first of all, we find the critical points, so we take the derivatives with respect to x and with respect to y here, and we set those equal to 0. And so first, when we find that y is equal to x cubed, and y cubed is minus x is equal to 0. To solve these equations, we substitute y equals x cubed from the first equation into the second equation. And so what we get then is 0 equals x to the 9th minus x. We factor that out, and this will factor into x times, this is x to the 4th minus 1 times x to the 4th plus 1. And then that will factor further into x. This is x squared minus 1, x squared plus 1, and x to the 4th plus 1. Now, this has three real roots, and the real roots are going to be 0 and plus or minus 1. These give imaginary roots. So the three critical points are 0, 0, 1, 1, and minus 1, minus 1. And we get that by substituting up here. Now we're going to calculate the second partials and find the expression d of xy. So second partial with respect to x, we're taking the derivative of this is going to be 12 x squared. The cross partial is going to be minus 4. And the derivative with respect to y is going to be 12y squared. And so this is going to be, I substitute in, I get 144 x squared y squared minus 16. So when we plug that in, we find out that for 0, 0, that it is minus 16, that is less than 0. It's greater than 0 for these two. So that means I have to evaluate the second derivative with respect to x each time. And so what we find is that this point here is a saddle point at 0, 0. And since d evaluated at 1, 1 is 128 is bigger than 0, and fxx evaluated at 1, 1 is 12 bigger than 0, we can see that this f of 1, 1 equal minus 1 is a local minimum, and similarly this is also a local minimum. So the graph is going to look like this. We have 2 local minimum, and that is what we have for this solution, and there's the graph. Now we can also think about a contour map of this function, and you can see what happens near the points 1, 1 and minus 1, minus 1. They're oval in shape, and indicate as we move away from those in any direction, the values of f are increasing. So the level curves near 0, 0, however, resemble hyperbolas. See, these are hyperbolas like. And they reveal that as we move away from the origin, where the value of f is 1, the values decrease in some directions but increase in the others. Thus, the contour maps suggest the presence of maxima and saddle points that we already have found. So this is the contour plot, and this gives you an idea of what a contour plot is going to show you when we're going from for minimums and for saddle points. Here's another problem for you to consider. Find and classify the critical points of the function z equals f of xy equal 10x squared y minus 5x squared minus 4y squared minus 4 or minus x to the fourth rather minus 2y to the fourth. And also, in addition to finding and classifying the critical points, you're to find the highest point on the graph of f. You know what to do. Let's see how you did. So again, we take the first derivatives with respect to, here is x and here is y. And so we have to solve these equations where these are equal to 0. Here we factor out a 2x. And here we have another one to find. So we see that from equation 4 here that x equals 0 is a solution. And when x is equal to 0, we find out that y is also equal to 0 when I solve that, and here there's no real solution, so it's 0, 0. In the second equation, we get x squared equal 5y minus 2.5, and putting this into equation 5, which is over here. For the x squared, that gives us an equation simply in y. So we have 25y minus 12.5 minus 4y. I can combine those terms. Minus 4y squared is equal to 0, so we end up with this cubic equation. Actually, that is 4y cubed there. So this is 4y cubed minus 21y plus 12.5. Now, solving cubics is harder, but here we solve these approximately. Find that there are 3 real roots, so they're approximately 2.5, 0.6, and 1.9. And we could use Newton's method or something like that. But now what we're going to do is we're going to calculate the values of fxx and d for those various values for those critical points. And we get that this one is a local maximum. That's a local maximum, and that is a saddle point. Figures 7 and 8 give two views of the graph of f, and we see that the surface opens downward. And this can also be seen from the expression for f of xy. The dominant terms are both negative, and so those clearly open down. Comparing the values of f at its local maximum points, we see that the absolute maximum value of f is at plus or minus 2.64 and 1.90, and when I plug that in, I get approximately this. So the highest point is 8.5 is the highest point on the curve, and it's achieved at these values. Now, when would you use families of surfaces like that? Well, many surfaces can be varied to suit a particular purpose by varying certain parameters. These parameters can affect many properties of the surface, including where the local minimum or maximum occurred. For example, and we've already talked a little bit about this, but manufacturing costs can be approximated as a function of the amount of material used and the amount of time needed. And this is having to do with a Cobb-Douglas equation. So factory managers can vary the function's parameters and use first-order partial derivatives to find potential minimum cost values. Likewise, chemical reactions change according to many parameters, including amounts of the reactants and heat. Chemists must consider many factors when planning reactions. Varying the function's parameters and viewing contour maps help with such analysis. And last, from the physical sciences, physicists consider many factors when plotting the path of a rocket launch. The path varies according to the fuel type, wind, fuel consumption rate, and many other factors. Varying these parameters and visualizing the corresponding surface helps find ideal conditions. So there's much to be said about analyzing families of surfaces. The 5 critical points that we talked about before can be shown in red, and we see as before where do we have relative maximas, minimas, and saddle points. And from contour maps, we see that contour maps show many level curves for a particular function. These maps help estimate the location of maxes or mins of the functions. So people who make maps, which are called cartographers, use elevation to create topographic maps. Level curves of a function for elevation makes it easier to estimate the location of mountain peaks, which represent the local maximum points for the function. Similarly, meteorologists use contour maps to present temperature forecast. The lines of constant temperature help indicate the direction in which the temperature is increasing or which direction it is decreasing. And population density maps are used by sociologists for many studies of urban and rural behavior. These maps are approximations of contour maps for the population density functions. Contours and coloring can make it easy to identify local maximums and minimums. Here's another application. Here what we're supposed to do is find the shortest distance from the point 0, 1, minus 2 to this plane 1, x plus 2y plus z equal 4. You know what to do. Let's see how you did. Okay, well this is the distance formula, but if x, y, z lies on this plane, then z is equal to this. So we can make that substitution into this equation for z getting this. And we can minimize d by minimizing the square, which is a simpler expression. So what we're going to do is we're going to square both sides, and we'll be seeking to find the minimum of this. So what we do then is we're going to take the derivatives of this new f of x, y. With respect to x, getting this, and with respect to y, getting this. Please make sure that you understand these calculations. And so we have this equation and this equation, and there are two equations and two unknowns. Both of these are linear equations which we can solve, and solving them simultaneously we get the critical point is 11 over 6 comma 5 over 3. And then we calculate the second partial with respect to x and with respect to y and the cross partials, and we have that our d of xy is bigger than 0 and f of xx or fxx is bigger than 0. So by the second derivative test we know that we have a local minimum at that point. And so what we can do is we can take that point, plug it into the distance formula, and we get that the minimum distance is achieved at those points 1, 0, minus 2, and it is 5 square root of 6 over 6. And we could have solved this using vectors as we did in an earlier chapter. We now come to another example, and I didn't give you a little work element here, but you know what to do. So a rectangular box without a lid, and that's different than the problem we had before, is to be made from 12 square meters of cardboard. Find the maximum volume of such a box. Now this is different because we're trying to maximize the volume and we're given the total surface area and there is no lid. You know what to do. Let's see how you did. Oh, here it is. I had it on this one. Okay, so what we're going to do then is we're going to remember that the volume is equal to x times y times z. But now that's the thing we're trying to maximize, but now what we have is the surface area is constrained. So the surface areas that we get, we have the other two sides, but we only have the bottom is equal to 12. So we solve this equation for z. We only have one z, and we get z is equal to 12 minus xy over 2 times x plus y. And so the volume, when we take that for z and substitute it into the volume equation, we get this expression. So now we're going to compute the partial derivatives for this expression. So the partial with respect to x, we get this, and with respect to y, we get this. So both of those have to equal 0, and x can't be 0 or y equals 0 because we would have a 0 volume, so we have to solve these two equations simultaneously. But if we solve these simultaneously, we get that x squared equals y squared, and that means that x equals y since they're both positive. And so what we can go back and do, we take x to be equal to y, and that tells us that z is equal to 1, x is 2, and y is 2. So it's 2, 2, and 1 is our solution. And we could use the second derivative test again to show that this is a maximum of v. Thus, v is equal to 2 times 2 times 1 is 4, and the maximum value of the box is 4 cubic meters. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.